Thanks for attending the fifth installment of my effort to convince you of how we can use astroparticles to understand our world. Today we're going to be talking about cosmic rays impacting life as we know it, and maybe at the end we'll introduce ideas and active research into how it may have played a role in the origin of life. So just to go back to a little bit of review of what we mean by different lenses. When you look at the night sky, you look at the Milky Way in optical with your eyeball. You can also look at it through a different lens called radio, and we talked about also looking at the Milky Way through X-rays. And what we showed throughout the past few lectures is that with X-rays, for example, you can see through opaque objects. So in the Milky Way's case, you can see through the visible gas that's in your way and make measurement of the millions of degrees hot gas in the center of the Milky Way. With radio waves, we observed that there were different processes and revealed hidden structure inside the Milky Way center, right? And there's a host of other electromagnetic waves that can be used, and so basically you're putting on a different lens every time you use a different telescope. And for the radio waves, right, we have the shortest wavelength, or the longest wavelengths, the lowest amount of energy, but we also talked about using high energy electromagnetic radiation like gamma rays and particles themselves, right? We talked about using muons and other kinds of radiation and what that teaches us by putting on lens by looking at those particles, right? And so I introduced you to the idea of cosmic ray muography, where you can some projects like this example uses muons, cosmic ray muons, to look through hundreds of meters of rock to make measurements of the inside of volcanoes, something X-rays cannot do for you, right? We also talked about neutrino tomography, where you use neutrinos that are measured by this experiment called IceCube at the South Pole to actually make a measurement of the density profile throughout the entire Earth, right? So basically trying to use neutrinos like X-rays, but probing the entire structure of the inside of the Earth. And last week we introduced this idea of how cosmic ray air showers can trigger lightning with these tremendous gamma ray flashes that were measured above thunderstorms, and the kinds of very, very recent results regarding cosmic ray air showers potentially seeding and triggering lightning and thunderstorms. But I haven't yet talked to you about the actual mechanism really that produces or accelerates those cosmic rays to the energies that we need them to in order to use all of those particles and understand the world with them, right? And so one of the cosmic ray accelerators, or the sources of cosmic rays, are supernova remnants, okay? And so the supernova remnant is the aftermath of a powerful expansion of material around a star that has already exploded. So on the left, you see a supernova, which is the actual explosion, or at least an animation of one, sorry. And this is one type of supernova. This is not all of the kinds of exploding stars that we know of. There's many different mechanisms. There's different kinds of supernova that go off, right? But the thing on the right is the remnant of that supernova. It is the expansion of the shockwave, all of the energy that was produced that is accelerated, that we think is accelerating all of these cosmic rays to very high energies. Okay? And so one example that I'd like to point out is within the Milky Way is a supernova remnant called W44, or given the title of the nomenclature here is W44, where the remnant itself is this large region on the right, but an X-ray emission shows you the hot gas that is expanding from the supernova here. The pulsar is left over. And Fermi Gamma Ray Telescope has actually made measurements of this region and shown us that it's probably, and it seems like very strong evidence, that there are cosmic ray proton interactions because there's a significant amount of pions. And as we've discussed, pions are produced by interactions of cosmic ray protons, right? And the amount of energy that Fermi Gamma Ray Telescope has measured and the energy range, the extent of it, illustrates that this is probably what's going on with supernova remnants, acceleration of high energy particles in the Milky Way. And so if you remember from last week, what we talked about was cosmic ray particles not extending just to energies of like peta electron volts or thousands of tera electron volts. We talked about electron volts a lot now in this lecture series. But we talked about cosmic rays that extend all the way up and have energies that are on the order of 10 to the 20 power electron volts, right? So that's so much ridiculous amount of energy, and I encourage you to go back to last week if you want to explore those particles more. But basically, you can divide this cosmic ray spectrum, where the y-axis is the rate and the x-axis is the energy of those particles, into galactic origin that only seem to be able to accelerate cosmic rays to some cutoff energy, and extragalactic origin, which are more exotic things like supermassive black hole, active galactic nuclei related phenomenon, right? So we can divide and we can think about the kinds of particles here that we've measured at Earth coming from two distinct sources. We have the galaxy and we have outside of the galaxy, right? Different energy reaches. And last week I talked about that flux of primary cosmic ray particles. I talked about how cosmic rays at higher energies are rarer, they're less frequent, right? And so what I want to show you next is the measurement of that spectrum of cosmic rays with many different experiments, including those on the ground and in space. And you can see that over this x-axis in energy and this flux, there's a huge fall off, right? There's much less of these particles at extremely high energies compared to those at the smaller energies. And so I introduced you to the idea of this flux, meaning if you take a given area and you count for a given time, seconds, for example, from a very specific direction, how many particles did you just measure at that energy, right? That's the idea of a flux. And so we said that for these extremely high energy particles, the flux is so small that you would have to sit in space and hold out your hand for 6 billion years to catch one of these 100 exa-electron volt, or 10 to the 20 power electron volt cosmic rays, if you wanted to catch it in your hand. 6 billion years, because the flux is just so small. Now, on the scale of the Earth, we measure them, right? We measure their interactions in the air. But if you wanted to put a detector in space that was this size, not going to do it, right? And so the idea that I introduced is, and what I'll talk about in the very last lecture of this series, is that those particles are accelerated somewhere in the universe to these extremely high energies, right? And that's something that is still undergoing research. But if we come back now to the Milky Way, we focus on cosmic rays accelerated in the Milky Way. The picture I want you to have is, this is our Milky Way. There's many different stars. There's supernova remnants that go off in bursts. And inside of, for example, the galactic center, you have some stars that are going off producing supernova, but then those remnants over a long period of time continuously produce a bunch of cosmic rays in the center, right? And that can happen actually anywhere inside the Milky Way, but specifically we think in the active center of the Milky Way, that's where it's happening, right? And so this results in a sea of cosmic rays that fills the Milky Way galaxy. And the solar system where we live, right, where the Earth is present, the solar system sits inside of that cosmic ray sea, okay? And so what we think is happening is that this cosmic rays in the galaxy that we seem to always be measuring at the energies of hundreds of GeV to a peta-electron volt, millions of GeV, giga-electron volts, that there's different bursts of supernova remnants that continuously spit out some energy, but they're remnants that exist for many thousands of years, continuously produce these cosmic ray particles, right? So we have a sea of cosmic ray particles that seems to just be how the Milky Way interacts in energy, right? Those stars die, the remnants of those stars produce cosmic ray particles in the Milky Way. And this is a lot of what I'll focus on next week about cosmic ray acceleration in the Milky Way and how we can use isotopes to help us understand it better. But for the sake of this lecture, we're actually going to talk about cosmic rays as radiation. And so when I say radiation, what I mean is that picture that I presented in the very first lecture, where we have alpha particles, which turn out to be helium nuclei. We have electrons, which are beta particles from beta decay. We have X-rays, gamma rays, even muons. And at first, they were characterized by how much material they went through, right? And we can see that higher energy particles typically go through or penetrate through more material. But each type of radiation here, right, interacts differently through different processes. Muons, for example, or electrons, have this ionization process because they're charged particles. They go through the material that's made of atoms, and they ionize those atoms and produce electrons and other ions of the actual atoms themselves, and that's how they deposit or lose energy, and so eventually they stop, right? There was also this process called Bremsstrahlung that I just wanted to highlight and mention from the second lecture of the series. And this is actually, historically too, has been a hazard with radiation research, right? It's when you try to do research on this radiation, it's a hazard because of the phenomenon that it's depositing energy but also penetrating. It goes through your skin and it can go deep into your body and then deposit its energy there, right? And so some types of radiation are more harmful than others. And so that's sort of where I want to begin the focus of how cosmic rays impact life. So some biology instead of physics now. Biology, as a lot of what we do in research in biology really comes from thinking about DNA. And so DNA here, what I talked about in the second lecture was the discovery of double helix structure, which was called Photo 51. DNA has a double helix structure, but the radiation itself actually impacts or damages your DNA. And DNA repair is actually common. It's something that always happens. It's something that is related to the evolution of life as we know it, is that the fact that DNA can be repaired was useful to the survival and therefore the evolution of the different kinds of organisms on Earth. And so this double helix structure is very significant to that repair. You can have low energy radiation, such as low energy electrons, which create ionization clusters, depositing energy, but this kind of radiation is actually called, what in the field they call it linear energy transfer, or LET, right? And so this is where this radiation is crossing through material, goes through the molecules of DNA, deposits its energy there in the form of ionization, just like I talked about on the previous slide. But usually, those electrons can't then break both sides of the DNA. And I'll talk more about this one on the next slide. There's also high energy linear energy transfer particles. So for example, alpha particles, right, are beefier in the sense that they can deposit more energy as they travel through DNA. And in fact, they have clustered ionization events that break both sides of the DNA, right? And so this is where there's a higher risk of mutation and cell death in DNA simply from different kinds of radiation. X-rays are not like this. They're more low LET. So an example of that in DNA, a lot of people do research. You have DNA in all of us, in all of our cells, is really suspended in water. 60% of humans is mostly water anyway, right? But a significant fraction of the DNA, or all of the DNA really, is suspended in water. And so what you have is this radiation coming in, interacting with the water, ionizing it, and resulting in different ions in the water, and this is an active area of research, which then impact your DNA. And so that's the way that the energy of radiation impacts the structure and leads to mutations and cell death, right? This is one example of that, and I'm summarizing basically an entire research field to convince you here that the different kinds of radiation, such as X-rays, gamma rays, and low-energy electrons, are this kind of radiation impact to life, right, to DNA. But this is energy that's spread out in space, and actually most of that energy that spreads out from X-rays and electrons actually comes from Compton scattering. So I can say that I've named him 5 times in a row, if anyone's keeping track of the bet. And we've talked about Compton scattering before, right? We've said that X-rays come in and ionize electrons off of the atoms, right, and scatter, right? So the X-rays don't deposit energy in clusters. They mostly can only break single strands, and that's called a single-strand break in DNA. It's literally called an SSB in this research field, right? But you also have that ionization from those knockoff electrons here, these electrons that come from the Compton scattering of X-rays, can ionize the atoms, and those atoms, as we said, are suspended in water. And so the atoms that make up DNA are constantly being bombarded by this radiation actually here on Earth. And that's actually how most of DNA, as far as we can tell, appeared to have evolved into the structure it exists today, is because it's so good at repairing itself when only one side that's exposed to that low LET radiation is able to repair itself more than not. But now we have to talk about high LET particles. This is where most of that energy is actually deposited in a narrow track, because those particles are usually so much heavier, they don't scatter, and so they're constantly ionizing in a small region, and it can actually break both sides of the DNA, right? And so this leads to a lower chance for repair, and so really we have particles like protons, neutrons, and nuclei of different elements. So the example shown at the top here is an alpha particle, which is a helium nucleus, and it's ionizing this narrow track around the DNA and producing breaks. And so the linear energy transfer, or LET here, quantifies for you how much energy per unit length. And you can see X-rays about 2 gives you a little baseline to orient yourself for this new unit, probably. Maybe some of you know much more about this than me, and you can school me on it afterwards. But then you have 10 MeV protons, slightly higher than those X-rays. If you come all the way down here to alpha particles, significantly more energy per unit length, right? And then you can even look at iron ions, which I'll come back to. So much more, because they have so much more nuclear charge. And this alpha particles are actually used in medicine a lot because they can penetrate and therefore destroy cells that are maybe harmful in your body by penetrating, by being produced in your body and then penetrating those specific cells and breaking the DNA in there. So this is something that can be used if you understand it, but something that we have to be aware of and be careful with, right? Is that these are different kinds of high LET particles, high LET radiation. And so one example to produce those alpha particles is radium, and I'll come back to radium later. Excuse me. All right, so LET for different types of radiation here, this table that I showed you on the previous slide, can actually be sort of thought about like this. You have this linear energy transfer, this energy deposit per unit length on the y-axis versus the energy of those particles. But each particle has a different charge and a different mass and different interactions. So electrons here are this dashed line. They don't have as much energy deposition per micron here, right? So they're low LET. But protons at this energy have a significantly more amount of LET, and then alpha has even more. The helium nucleus has even more. And so this radiation exposure to your cells, to your DNA, to yourself, right, or to other living organisms can create damage. All right? Our DNA is able to repair itself, but there's actually 3 different kinds of options that most of the research in this field talks about. It's you either have the cell die, you have it repair, or it mutates. And so those are your 3 options. This is what happens when when you expose your DNA to radiation, right? And the repair is more than often the case for what happens to us here on Earth. And then there's different types of radiation impact, such as deterministic, where you have burns or serious illness after being exposed to radiation. You can have stochastic processes that happen, such as mutation that leads to cancer, which can be passed down to offsprings. And a lot of active research in this field comes to the personal aspect, where each individual seems to be more sensitive or less sensitive compared to others. There's aspects to the sensitivity of a person's cells and DNA and their biological impact from it seems to be very individualized. And so this is a huge research field, mostly because of going to space, right? And so I want to sort of introduce you to the history of how we understood this radiation, which helps us appreciate where we're at today in terms of how this radiation impacts our health. So originally, there was this skin arrhythmia dose, SEDs, was a unit, an actual unit that was used when Röntgen first discovered that X-rays would be useful medically, right? And then the discovery of X-rays. What they would do is they would literally expose their hands, the scientists or other research assistants, I guess probably too, to X-rays and say, yeah, I left that on for like 5 minutes and now I have a huge burn, so that's a high SED. Or 2 minutes and not so much. That was literally their unit that was used. But it was pretty subjective, right? Because it's saying, what is the minimum amount of radiation of this X-ray to give me a burn? And then there was the famous radium girls from 1917. I think there was a recent movie about that within the past 20 years, or maybe even sooner, where radium that I talked about with those alpha particles was actually used in different manufacturing processes to make sort of like glow-in-the-dark related items for sale, right? And then there's also the Slotin accident, where at Los Alamos, just after World War II ended, where a research assistant, Slotin he was actually here at UChicago, I believe, but in like the mid-1930s before with working as a research assistant with Enrico Fermi. But basically, he actually had some accident where a core of plutonium, I think, went critical at Los Alamos, and he died 9 days later after being exposed to that awful amount of radiation. So this radiation was determined to be lethal, right? And actually, Hermann Muller in 1946 won the Nobel Prize in Medicine for the discovery that this X-ray doesn't just cause these burns, it actually can cause mutation of cells, mutations of different species. I think he discovered that around the mid-1920s. So long before, I think it was a few years before the understanding that DNA was a helical structure, we already knew that X-rays could cause mutations in biology. So if we keep going with this, we have these SED burns, right, which is a unit, and then we became a little bit more sophisticated and produced what's called a RAD, or a radiation absorbed dose, right? And this is basically what I've tried to present to you is the amount of energy that's deposited per unit length, right? So if you expose a set amount of material to the radiation, how much energy does it actually absorb? That was like a RAD. However, this was not so useful when talking about the impact on human life, because 1 rad of X-rays is not the same as 1 rad from alpha particles. As we said, the impact to the DNA, right, matters significantly to whether or not you have a higher risk of mutation or disease or cell death, right? And that's because of that clustering that I talked about. So later in like the 50s, we introduced this new unit called a REM, or a Röntgen equivalent man, which basically took that rad and said, some particles are much worse for us than others, right? Some kinds of radiation are much worse than others, even if they deposit the same amount of energy. And so that meant that alpha particles had a high quality factor, and so have a higher REM, even if they deposit the same amount of energy as an X-ray. And so nowadays, what we talk about is the sievert usually. Okay, sievert is the unit that was introduced and accepted in 1980 as like the SI unit for this kind of radiation dosage. And you can see from this map, from the CDC, I think, yeah, I'm pretty sure this is the CDC, shows you the different kinds of things that provide you the radiation dose that corrects for the kinds of radiation it is, the energy it's at, and how much gets absorbed by the cells in your body, right? And so you can see one of them specifically that I'll talk about next, obviously, is cosmic radiation, right? Here it's about 0.3 millisieverts. So that's what I want to go to next. So we remember many times, I think every lecture probably now, I've mentioned the muon just because I like it so much, but the muons are actually low LET. That's why I like it, because it doesn't hurt me. They're highly penetrating and they deposit energy over such a large distance. And there's a lot of muons, right? We talked about all those cosmic rays producing basically a rain of muons below at the surface of the Earth. And so the amount of the dosage rate from muons only that you get in the human body per year, your annual dose, is about 0.4 millisieverts. So the unit you have to have in mind here is a millisievert, right? This is 1/1000th of a sievert. But it's actually less than 1/1000th because it's 0.4, right? It's not even half a millisievert. Now this is about the same as if you ate a bunch of bananas. So over the course of a year, the average person, I guess it's probably the average, not the median. It would be funnier if it was the average, because then someone who eats like a banana like 4 times a day, every day of the year, probably has a huge amount of potassium exposure. But potassium-40 in bananas actually gives you about the same amount of annual dose of radiation. So if you're like me and you eat a banana probably at least a few times a week, right, you have about the same amount of radiation exposure. So the total, though, from cosmic ray muons, from your banana eating habits, and other kinds of radiation, such as the radiation from rocks, and etc., leads to an average person having about 2.5 millisieverts per year as your annual dose. Okay? and only 20% of it comes from cosmic radiation. So that gives you a baseline. That gives you the orientation you need now to think about how much radiation we're talking about when we go to space, right? And so first, if we go to higher altitudes, right, recall the atmosphere is in the way, those cosmic ray particles that produce all those muons at the surface that we just live in, right? We understood that those particles came from space. We understood that as we increased in altitude, we ascended on these balloons, we measured more radiation, higher energy particles, right? And so the risk of damage increases as you go up in these balloons. And so you have at the surface, you have muons, which are low LET, but as you go up in altitude, maybe to airplane or balloon altitudes to actually measure these particles themselves, they have both higher energy and they're more likely to be protons and nuclei of different atoms, and so I'll talk about that next. So these cosmic rays, I've sort of tricked you, and I'm very sorry about that. Cosmic rays are not just protons. I kind of said that just because I didn't want to deal with it at the time, but now I have to overcome that and say only 90% of cosmic rays are really protons. And so the measured spectrum that we have, all these different kinds of measurements over different energy range, actually shows you we've measured the composition of cosmic rays, and we've measured some of them to be helium nuclei, carbon nuclei, oxygen, all the way up to iron, right? And so that means that the helium, the alpha particles, are actually inside the cosmic rays as well. The other 10% is those alpha particles, okay? And so you can even have iron nuclei at high energies. And remember, the LET here, the higher the charge of the nucleus of that radiation, much more risk, right? Because it's depositing so much energy in a cluster and impacting your DNA. So the danger in space actually comes mostly from the higher charge or high Z particles, the high Z cosmic rays. Okay? And I think I talked about this once before, but just to really drive the point home, you can have an element, right, in the periodic table identified by the number of protons. The nucleus of that atom is the number of protons that identifies the element. But inside that nucleus, you can have different number of neutrons, right? And so you can have a different number of neutrons, which corresponds to different isotopes. But here I'm talking about just the charge of that nucleus, just the charge of the cosmic ray, right? And so higher charge leads to more damage to human health. And at higher energies, you can see one interesting feature here. At higher energies, this LET falls off, right? The LET amount goes down, and so alpha particles at this energy range are pretty damaging, but down here, not so much, right? If they're higher energy, they don't seem to deposit as much energy per unit length. And that's actually a relativistic effect that's well understood. But still, radiation loses this energy, right? It loses it if it's traveling faster. It actually doesn't lose as much until, for the sake of this lecture, that's what we're talking about. At very, very high energies, then it loses a lot of energy. But for the sake of this lecture, there's this nice feature that higher velocity, less LET. Okay, so just to summarize that for everyone so far, what I've talked about is the danger from cosmic radiation, because as you go up, you're exposed to higher charge particles, right? You're exposed from protons to the nuclei of different cosmic rays, and you have higher energy. At higher energies of those cosmic rays, you might have less energy loss. And actually, we use this idea in medicine. It's pretty interesting to think about. But if you take in what's called proton therapy, if you take a proton at some energy, it doesn't lose so much energy, and so it can penetrate your skin and not hurt you, right? It's low LET. But as it goes through the skin, it actually loses enough energy, and through your bones, it actually loses enough energy to now all of a sudden become, inside of you, a high LET particle, right? It's slowed down enough to now become a high LET particle, and that's a focused way of doing proton therapy, where now that it's high LET, but it's already at a specific depth inside your body, it can actually destroy targeted cell regions, right, such as tumors. And so this is actually a very interesting point about different proton therapies. But I don't want to lead you astray here. When we talk about cosmic rays, we're talking about also iron nuclei that have so much charge that it doesn't matter that they're lower LET at higher energies, because they already have so much charge, they're always basically high LET particles, right? They just destroy everything in their path in dense material, leading to so much ionization, so they're always basically high LET particles. Okay, so this actually allows you to rethink and be grateful for the atmosphere of Earth in a different way, other than the air you breathe, etc. Is the atmosphere is actually a shield to this radiation, right? These cosmic rays don't make it to the surface; they interact high in the atmosphere, and so you're not sitting in that radiation by being on the surface, right? This picture that I've shown many times now is this cosmic ray, maybe an iron nucleus cosmic ray interacting in the atmosphere, and you sit down here in lower energy particle C, right? And the interactions in the atmosphere actually distribute that energy in form of muons, which is not so harmful. And so in this research field of the amount of radiation dose versus altitude, we actually see that at sea level, altitude of 0 here, most of the radiation that we get is from muons, if we're just talking about radiation dose from cosmic rays. But as you go higher up in altitude, eventually, such as up to like 20 kilometers here, you end up getting different kinds of radiation, right? Because you're escaping out of that atmosphere, right? The atmosphere is no longer as much of a shield to you. And so this is actually why pilots, on average, have a higher radiation dose, annual dose, than the average human. So if you're a pilot in the room, right, you have about a little bit more than twice the average human's annual dose because of being at higher altitudes for longer periods of time. And this extra radiation, though, is not coming from eating more bananas, right? Pilots might, on average, eat more bananas, I don't know, but really, it's from the fact that they're at higher altitudes, right? The cosmic radiation up there is more dangerous. Now, it only leads to about 7 millisieverts per year, but that, over a long career, can be a significant difference in the terms of a pilot's health. And so one of the particles that you'll see mentioned here is that at the altitudes specified by this red arrow, where pilots, usually fly 30,000 feet or so, neutrons are actually the kinds of dangerous radiation that pilots are exposed to. Now, then you could think about going to even higher altitudes, right? And so that's what happens in astronauts. They have even less atmosphere, and so they get even more radiation dosage. And there's actually an interesting sweet spot of the most radiation, and then it kind of drops off, but I'm not going to talk about those details. Now, there's another shield that exists besides the atmosphere for those astronauts in space, and that's the magnetic field of Earth. Okay, so this is the image that I took as like this lecture series. Beautiful artwork, but basically it shows you a bunch of radiation funneling towards the north and south pole of the Earth, and that's because of Earth's magnetic field. But the image on the left sort of illustrates the point here. You have Earth with its magnetic field lines shielding us from cosmic rays and even other kinds of radiation called solar energetic particles. So you can think of the magnetic field of Earth as also a way to shield from this radiation. I think this is a video that shows those kinds of particles, cosmic rays or solar energetic particles, being deflected by the magnetic field. And there's interesting research in what happens with the way our magnetic field interacts with the sun's particles. When the sun is more active, then that shielding sort of changes and you can get more or less radiation at Earth, right? And actually this leads to funneling of cosmic rays to the north and south poles, which leads to, let me see. Oh yeah, this shows you those cosmic rays sort of start to follow the field lines and produce at the North Pole, where the magnetic fields bend inward, give you the northern lights, the aurora borealis, right, and the southern lights too. But this also, back to what this cosmic radiation means to life, actually leads to the fact that higher latitudes you have more cosmic ray radiation. And so ISS astronauts actually receive a higher dose of radiation, on average, than those astronauts on the space shuttle. So you can see the different orbits here. The ISS orbit is more highly inclined. It spends more of its time closer to the pole, so it's being exposed to more of the radiation from the simple fact that the Earth's magnetic field funnels cosmic radiation there, right? And so ISS astronauts actually get about 0.5 millisieverts per day. So that's 180 millisieverts per year, right? That's a significant jump over the pilots, which was already about twice what was an average mortal on Earth. So if the cosmic rays are fast enough, though, those cosmic rays with high enough energy actually don't care about this magnetic field and they can punch through. And so this is the Earth's field as a shield being on the order of only a few milligauss. You could imagine if the field were stronger, you could shield or deflect even more radiation, right? And so this is obviously leading to the idea of using magnetic fields or other kinds of fields as shielding from radiation with space travel. Okay, so let's continue this journey going from, surface 2.5 millisieverts, and then we have per year, then we have pilots, now we have astronauts, which is a huge jump, but they're still inside that magnetic field. And actually, if you remove the atmosphere completely and go from low Earth orbit to, I don't know why I didn't spell that out for you, sorry, low Earth orbit to these lunar missions, you can still get some protection from Earth's magnetic field at the moon, but you don't get the atmosphere at all anymore, right? And you're exposed to much higher radiation, that radiation coming from the sun and cosmic rays. Now, on different lunar landers and orbiters, we've actually measured the kind of radiation that has been that is constantly bombarding the lunar surface. And so here's an example of one of those measurements where a cosmic ray passes through a detector on one of the orbiters. I think it was the lunar reconnaissance orbiter, and it measured about 1.3 millisieverts per day. Okay, and so this was the crater instrument on LRO, but they actually utilized and invented a detector that was a human tissue equivalent plastic, so they could measure basically with the same amount of material as human tissue to make an accurate measurement of that radiation dose over a long period of time, over many different measurements. And so this is another jump from the astronauts, right? So the ISS astronauts, this is 2.5 times that dosage rate. So overall, if you spend time on the lunar surface, per day you're exposed to 200 times the amount of radiation from Earth's surface. And this is us going from the surface of Earth to low Earth orbit where the ISS astronauts are, escaping the atmosphere, maybe still being shielded somewhat by the Earth's magnetic field. And you can see at the bottom here the extent, the distance scaling that we've gone and measured this radiation right here at the moon. So just to give you a perspective of that distance, right, you have the ISS, which orbits the Earth at 400 kilometers in altitude, and lunar orbit of that measurement that I showed previously was at 350,000 kilometers high, right? I invented this new unit called a gigameter. I don't think many people usually use gigameter for some reason. I think it's a great unit. This is almost half a gigameter. I think it's a wonderful unit to use. But usually you see it in terms of thousands to millions of kilometers, which maybe is better for some people, but I prefer gigameter. Anyway, so if the ISS was the building across the street from us, if that's where the ISS orbit was, if that's how close you were to it, then you'd have to still drive all the way to Kenosha to get to the lunar surface, to get to the lunar orbiter, sorry. Right? And so Kenosha, if you don't know, is in Wisconsin. I guess if you're a local to Chicago, you probably know Kenosha. I don't know Kenosha, sorry. But that's one of the popular things to think about 60 miles away, apparently. And so what we've said is, by going that far away from the Earth, you escape the shielding of the atmosphere, but you do still have some of the Earth's magnetic field, but you have much higher daily radiation doses. And most of it comes from, the stable part mostly comes from summing up or integrating all of these different cosmic ray particles, right? Where a significant amount of that radiation comes from these high charged particles simply because they have so much charge, they deposit so much energy as they pass through astronauts. All right, so this is as what's measured with lunar landers so far. I wanted to highlight, not next week, but the week after, Peyton, my colleague, will be here to talk about using cosmic rays to search for water on the moon. So please attend that lecture, and you can ask him, was Keith totally full of it when he talked about lunar landers, or is there actually a lot of research in that? Okay, so let's continue this journey, because a lot of people are investing a lot of time now in research about how we can get humans to Mars, right? And we've actually put a lot of we've had many experiments, many different missions to Mars. One of those was the Curiosity rover, and it made actually deep space, what we call deep space measurements en route to Mars. So you can see here Earth at launch and the trajectory that it took, measuring the radiation along the way, and it found that that was about 2 millisieverts per day. So per year, right? That's about 750 millisieverts per year. The Curiosity rover itself had an instrument on it called RAD, or still does, I guess, RAD, which measured this radiation and found that Mars actually has, with its thin atmosphere, actually has a slightly lower, right, amount of radiation, 0.6 millisieverts per day, than the lunar surface. So it's slightly more protected simply because of its atmosphere, but it's obviously not protected by Earth's magnetic field, right? So this is about 220 millisieverts per year. So if you were an astronaut traveling from Earth to Mars, one of the biggest challenges is shielding astronauts from the amount of radiation that they would be exposed to, right? Because it's about a year to travel there. And so you're approaching this level of about 1 sievert, 1,000 millisieverts, 1 total sievert for that trip to Mars, right? Types of shielding are an active area of research to try to figure out how to protect those astronauts from this kind of radiation. Now, the other thing is, what about leaving the solar system, right? We've already lost Earth's magnetic shield. We've already lost Earth's atmosphere. What about leaving the solar system? And so something has left the solar system, right? The Voyager 1 and 2 missions actually, in 2012, Voyager 1 left what's called the heliosphere, or left the solar system. It's really hard to separate those two things. I think it left the solar system. It's now in interstellar space if it leaves the heliosphere. There's a debate about what that really means, obviously, but definitely Voyager 1 and Voyager 2 in 2018 left the solar system. And so you can see, here's the sun, here's where Voyager 1 and 2 roughly are, and there's this big thing called the heliopause, which is the sun's activity actually producing a bunch of wind that protects us as another shield from cosmic radiation. And so outside the heliosphere, Voyager 1 and 2, which have cosmic ray detectors on board and have been measuring cosmic rays, although at slightly lower energy than what I've mostly talked about here, they've actually measured cosmic rays outside the heliosphere. They also made a measurement of basically the fact that the charged particles from the sun that are at much lower energy are kind of like a solar wind. And so there's a region in space here, when you get far enough away from the sun, where the solar wind can no longer protect you. And so that means that as you cross that region, where the sun's solar wind, its pressure doesn't help you anymore, you actually get a jump of cosmic rays. And now we're talking at the energy of the cosmic rays is slightly less than 0.1 giga electron volts, so 100 mega electron volts. But basically they measured an increase of about a factor of 4 of that flux outside the solar system. And so this is proof that the magnetic shield, or the heliosphere is a shield from that cosmic radiation as well. And remember, a lot of the particles here are also high charge, right? So this is also a huge jump in radiation by going into interstellar space, right? Okay. So you can think of now, before you get to interstellar space, the heliosphere as this shield, right? And the solar system exists inside of it, and the sun's activity actually changes. So we have a video here, I think, that shows over time, this animation shows you all these cosmic rays bombarding the solar system just from existing in the sea of cosmic rays of the Milky Way. But as the sun's activity changes, it actually changes that heliosphere's ability to deflect or protect as a potential barrier to cosmic radiation, making it inside of the solar system. Okay, so to summarize, we've learned that as we go to space, we actually need to protect more and more from cosmic rays, right? And there's different kinds of shielding. There's passive, which is like astronaut suits, right? Which is a bunch of material basically in the way that allows you to prevent that radiation from actually entering your skin and instead be absorbed by the suits themselves. But there's also different ways of doing this where you orient your ship in certain directions and use the material in your ship to protect you from bursts of the sun's activity, which produces some more radiation. And this was actually done on the ISS in 2017, where they sort of oriented all the astronauts in the ship around a bunch of different equipment to protect them from a solar particle event, right? So a bunch of particles coming in. Basically, you can also think of this as a geomagnetic storm, right? But all of that is just a summary of passive shielding protecting you from radiation in space. There's also the active shielding, where you could use fields like the magnetic field of Earth or the heliosphere of the sun, right? But both of these are challenging. One is passive stuff is heavy, and as we probably know, it's expensive to go to space, and it's hard to get more material up there. So that's obviously one of the challenges. The other is energy. So you can't just plug into a wall outlet, right? You have to think about energy, different sources of energy in space, and so having magnetic fields and different kinds of protection that's active like that also is a challenge. But this is ongoing research where human ingenuity is at its best. From what I've seen, in my short career, it sounds like a wonderful place to be solving problems. And one of those one of those researchers illustrated the effectiveness of aluminum shielding, where they utilize, on the y-axis here is the effective dose, right, in millisieverts per year from aluminum shielding, using different models that include the measurements of galactic and solar particles, galactic cosmic rays and solar particles, over many different years of us measuring those radiations. And you can see different modeling actually shows you, with the same amount of aluminum shielding, of what's called, in this business, called a grammage, 2 grams per centimeter squared, different models of those particles and different measurements provide, sort of agreement, but a range of amount of effective dose over time. And you can see the sun's activity reflected on there too, right? You can see a change in the amount of dose rate that these astronauts receive. So this is an active field of research. So this actually leads to the safe dose evolution. So in the Apollo missions, the biggest concern, the biggest risk was not deemed to be radiation. And so there was actually very little or no guidance in the 60s for the amount of radiation that an astronaut would receive in space, whether or not they knew that it was probably going to be an issue, but they said, look, we got a lot of risks with this mission, so that's probably not the one we should think about. And actually, from one of the articles, this report on safety says, that the did not recommend permissible doses for space operations, noting the possibility that such limits may place the mission in jeopardy. Right? So if they started talking about how much risk to the astronauts from radiation would be, they feared that people would not want to do it, or that the government would decide it's not worth it, right? So in the 1970s, just a very short time later, when it became clear that this is something we need to start thinking about with safety, there was an invention of this called the doubling rule, which was basically, throughout the entire career of an astronaut, you should not be exposed to about more than 4 sieverts. That's 4,000 millisieverts over your career as an astronaut. But this was basically calculated from a rough estimation of doubling the chance of having leukemia later in life, right? And so this is where that came from. But this is also what led to more modern times, like the report of the age and gender shift, where it was determined that female astronauts are more sensitive to radiation than male astronauts, and different age actually matters significantly too. So this is that individualized risk assessments and personal aspect to radiation dosage that I mentioned previously. So I found this slide that was really interesting, so I just thought I'd throw it up there, which is from this annual meeting, the mission dose rate on the y-axis, this is a log scale by the way, showing you every astronaut, I think this is every NASA astronaut, and this is characterized by an index I, right? So this is like, you don't know which astronaut's which, but over different missions, Mercury missions, Gemini, Apollo, and Shuttle, all the way to ISS, you can see the amount of dose that those astronauts have been exposed to, right? And so I thought that was really interesting to show too, that this is something that is going through a lot of evolution and thinking, because it's going to be such a huge issue going forward, but already is for our wonderful astronauts right now. Okay, so I want to transition the talk from, the radiation hazard to humans to how does this matter if we're trying to search for life, right? This is a related field of research because radiation is a hazard. Do we think that it actually wipes out life, right? Because it's a hazard to us. Maybe other worlds that are exposed to much more radiation on the surface might not survive either, right? And so exoplanets, maybe you're maybe exoplanets is a new term for you. There's also called extrasolar planets. Exoplanets are planetary bodies that orbit other stars and other systems, right? Not the suns. So the solar system has 8 planets and many different bodies in the Oort cloud and the Kuiper belt, etc. But around other worlds exist. The first actually were 3 different exoplanets discovered near a pulsar, which was actually groundbreaking at the time because no one even thought in the mid-90s that planets could be orbiting a pulsar at all. Right? They thought pulsars were too extreme of a kind of object, too much energy and too intense. It would destroy or clear its neighborhood of being able to have planetary bodies. But 3 exoplanets were discovered near this pulsar, and those were actually the first two exoplanets ever discovered were around a pulsar. And so this is not a real picture. This is an artist rendition that I found pretty cool of those kinds of planets. It's unknown still to today if they have atmospheres, because we know that atmospheres are useful as a shield from this cosmic radiation, right? But the amount of radiation at the surface is probably extremely high simply because of the fact that it's near a pulsar, which is a highly energetic astrophysical object. So nowadays, if you fast forward 30 years, we've discovered over 6,000 exoplanets. So it seems like the number of planets that do exist is high, but whether or not they can harbor life is something that is an active research field. And that introduces us to the idea of a habitable zone, right? You have, here on Earth, we know that the sun's activity impacts those cosmic rays making it to Earth, right? And we know that there's the shielding from the Earth's magnetic field, the sun's magnetic field, the atmosphere. Can those kinds of ideas, can we predict or measure atmospheres and other stars' activity to say what kind of radiation environment on those bodies exist, right? And so the cartoon you have in your mind is take a different star than the sun, take a different planet than the Earth around that new star, and say maybe that star is emitting a bunch of radiation. If it's too radiative, we probably don't want to say that there's life there. We don't want to explore it, right? Or inversely, if it's very active, maybe it protects the cosmic rays, or maybe it protects this planet from those cosmic rays, and does it have an atmosphere? Maybe it shields them, right? And so this is an active research field as well to see if, and it is something that is very interesting going forward, is can we measure exoplanet atmospheres and also model and understand their stars' activity to model what kind of radiation environment they have. So this leads to energetic particle environments of exoplanets. So if you're interested in this, Dr. Rogers Lees is one of the leading researchers in this field, where, for example, this system with an exoplanet and a star that was very well studied so far has solar energetic particles. Because we've measured how much X-ray emission around the star, we know how much roughly radiation that star is giving off, and we know that this planet that we've observed has some kind of atmosphere, but it's very uncertain as to what extent. And so the question is, can you use the fact that this star has an activity level, and you roughly know the galactic cosmic rays that are coming into that system, can you model what the radiation environment would be like on the surface, right? And so the answer is yes, but it depends a lot on the pressure or the amount of atmosphere that exists. So this shows you the y-axis is the pressure, right? So if you're up here, you're basically at a high altitude. You can't really say the altitude because you don't know really, right, the extent of the atmosphere for that planetary body, but you know it roughly has some kind of atmosphere. So you can say the pressure, as the pressure is very low, you're really maybe high in altitude, you have much more radiation from cosmic rays and solar energetic particles. And this star's activity is actually pretty significant. So at a low pressure, you have a lot of equivalent dose, you have a lot of radiation dose. But as you move to higher pressures, closer to the surface of this body, you eventually get to a region where maybe the dose rate is not so much. And then here's 2 Earths. There's really only one Earth. One of these is, the left one I think, is the kind of dose rate that Earth observes at that pressure, right? About, 5 bars or 2 bars, sorry. About 2 bars. That's only from cosmic rays, and the magenta is both cosmic rays and the sun's activity as well. And all other radiation. So at the surface of Earth, this is all of the radiation that you would get. So that's about that 0.25 millisievert level. So you can try to look for, the radiation environment on other planets and say, maybe life doesn't like that radiation, but actually there's some interesting aspects to life on Earth with respect to this radiation, is that we found some life forms, even on Earth, actually like radiation. They thrive under intense radiation. And so there's one that was interesting in the 90s, was discovered in the walls of Chernobyl, which is this black mold that was growing at an extreme amount. It was shocking to everyone at the time that this was even possible. It was not known that different kinds of fungi could grow near radiative environments such as the accident site of Chernobyl. And so what seems to be the case is that this kind of fungus actually eats the radiation, kind of like photosynthesis, where you use light to convert to energy and therefore build yourself a wonderful plant, right? This is radiosynthesis. You take radioactivity and you use that to create energy. And so this is an active field of research as well that sort of, within the past 30 years, is something that was not known previously, right? And there's even research nowadays on using different kinds of different kinds of fungi in space, where if it likes this radiation so much, maybe it's useful, right? Maybe it's useful in space because it can actually eat the radiation in a sense and grow large structures. So you don't have to transport heavy materials to space. You can install a small amount, and then over many years, you get a lot more of this fungus that protects you from radiation, right? There's also, here on Earth, things called extremophiles, which is a wonderful term. I just really like that term. It reminds me of someone who goes snowboarding or jumps off of, rock climbing. You're an extremophile, right? But we've learned that things like tardigrades can withstand ridiculous environments, and there's many different interesting aspects, but I'm trying to summarize it on one slide here. We know that there's organisms on Earth that can actually withstand a ridiculous amount of radiation. These aren't the ones that eat the radiation, they just don't seem to care about it at all. I think the actual fundamental biology of it seems to be, is that their DNA can be repaired even if it has these double breaks. So it's fundamentally different inherently. The microbiology of it is fundamentally different than the kinds of things that harm us humans, right? But so this kind of different resistant organism called an extremophile, I'm not even going to try to pronounce that. I actually did practice, but I can't pronounce it, sorry. But it was observed to handle, without caring really, 1,000 times the radiation that's a lethal dose to a human, right? So it just can withstand any kind of amount of radiation, even more than those tardigrades. And actually, we found these extremophiles in a range of different sites all across the world, just here on Earth, right? So we're learning from here on Earth about the kinds of life forms that can withstand and how they withstand radiation, which is obviously one of the biggest challenges that we have for space travel. So then you can go on and search for life on other planetary bodies. And so it might not be life as you know it, right? One active field of research is using radiolysis on planetary bodies with a lack of atmosphere, because even though they don't have an atmosphere as a shield, they do have thick amounts of ice, or in the case of the moon, a amount of surface thickness, and then maybe some structure underneath that can harbor life, right, where it's protected on the top. And so this is, in this case, ionizing radiation such as cosmic rays and the solar particles, impact our DNA, but beneath the surface of bodies like Enceladus, we've actually modeled what kind of radiation those kinds of environments yield, maybe a meter or so underneath the ice of Enceladus. And so you have the idea that maybe your extremophiles like the fact that there's this ionizing radiation of the ice. And the kinds of research that's done here shows you, in very small amounts of depths, what kind of biomass can be accumulated, for example, on Enceladus. So if you have ice of a meter thick, just under a meter, you have a higher chance of getting life. You have a higher chance of keeping around this biomass. Okay, so then I'm gonna end with a really interesting puzzle, which is called the homochirality of life. And so this is something that you might have heard of, but if you haven't, I sort of have to walk you through using both your hands in this case. So if anyone doesn't have two hands, I'm very sorry, but for more than one reason. But in this case, what you need to do is think about the fact that in nature, what doesn't exist is left-handed molecular structure in biology. What does exist is right-handed. And what we mean by that is if you take the DNA here, the way it orients itself, it winds in a direction that if you curl your right hand only, your fingers curling in the direction of the helix, your thumb points up, and that's the direction of the twisting, right, of the double helix structure. Whereas the one on the left, your right hand doesn't do that. It goes the wrong way. This is a left-handed structure for the molecules in DNA, okay? And so this is actually a known puzzle that was, I think, first pointed out in like 1850, before the discovery of DNA, that the structure of different cellular life forms seems to have a handedness to it. Okay, this is a huge mystery. It's perplexing. But why does life exhibit this homochirality? Homochirality meaning, why does it seem to prefer being right-handed, right? And it doesn't really care if you're left-handed or not. It really cares about its molecular structure, right? So just to orient us a little bit more here, what is chirality? So if you take your left and right hand, you can't, under a mirror, superimpose them, right? They don't fit on top of each other. And that's exactly what happens with these molecules as well, okay? So an object that can do that, for example, is a bottle, if it's actually really symmetrical, right? Under this mirror image, it can actually be superimposed, so that's called achiral. But the chirality of it means that you can organize molecules to have a structure that's more like this or more like that, and there's a difference between them, right? And so those kinds of molecules on the right show you an example of an achiral molecule and the chiral molecule beneath it, and you can see really the only difference between these is the fact that this has an extra oxygen, which results in the fact that it cannot be symmetric under that what's called parity transformation. And you can actually think about this in terms of screws too. You can have left-handed threads or right-handed threads, right? And so really, just to get the point across here, there is a structure in microbiology to this aspect. And so actually around 50 years ago now, it's probably the 1970s, there was this hypothesis to explain this homochirality puzzle, which was that, well, we know electrons and anti-electrons can exist in different spin states. And so the spin state here is like your right hand or your left hand. It's where your thumb is pointing is the spin, basically, right? And you can have states of electrons that are left-handed or right-handed, and you can have states of positrons or anti-electrons that are left-handed or right-handed. And so there seems to be a way for the interaction of lefty electrons to selectively damage, so lefty electrons selectively damage or destroy molecules of one-handedness. And so the hypothesis here is that the origin of life may have been handed an asymmetry, right? Is that from these different kinds of electron spin states, you can get a different interaction that prefers one over the other. And so this doesn't even yet bring into the idea cosmic rays, but we're getting there. So you have polarized radiation. You have the spins of those particles. If they're as a collective, if that radiation has a spin direction to them, each individual particle has a spin, but if total all of their spins sort of align, that radiation can be thought of as polarized, right? And you have this polarized radiation that's incident on two different kinds of helical structures of molecules. You have the right-handed helix and the left-handed helix structure. And this polarization will change very slightly the kinds of interactions that undergo in those molecules, because those molecules are made of electrons, which have waveforms, or which have wave functions that depend on the spin, and so the spin of those molecules matters, right? The orientation of those molecules actually matters when it couples to the spins of this radiation. And so there's active research that suggests when we create not DNA itself, but the prebiotic molecular structures that make up DNA, or the sugars and the proteins that are involved in that process, when we create those in labs, we get these kinds of structures, left-handed and right-handed, just the same, 50-50. There doesn't seem to be a way for us to create a bias towards one-handed kind of molecular structure. All right, but if you expose it to radiation that has a spin, that spin does interact with the molecular structure. And the only force, there's four fundamental forces of nature, There's the electromagnetic force, there's the strong force, there's gravity, and then there's this weak force, which is actually the only parity-violating force. Parity-violating means it distinguishes between left and right. Every other force doesn't care about it. All right, and so Naomi Globus's research actively explores this fact. It says, well, cosmic rays can come in, like cosmic ray muons, and impact the evolution of life on Earth. Because those muons are polarized, and the anti-muons actually are polarized, because they come from the weak decay of pions that were produced in the atmosphere. And as we've said previously, right, the atmosphere produces a bunch of interactions of cosmic rays, which produces pions, which produces muons, and that polarization of those muons is then handed, right? It prefers to have left-handed or right-handed muons, and I'll talk about that in the very next slide before I wrap it up. And so basically this image here has a cosmic ray coming in, has this weak force which produces muons, and those muons interact preferentially with one kind of handed DNA versus a different kind that didn't survive in the evolution of life on Earth, right? But on the right here is the weak force itself, where you have a positive pion decaying to a positive muon and anti-muon, right? And the spin direction here is what is governed by the weak interaction. Okay, so to bring it back to the very first lecture, actually, we said that cosmic rays are positively charged particles. And so there was actually a preference to having muons, or anti-muons, over muons. Anti-muons were preferentially measured. There was an extra amount of anti-muons over muons, simply because you have positive cosmic rays impacting the Earth, like protons and high-charged nuclei. It results in a net positive amount of anti-muons over muons at the surface. And so this positive excess of anti-muons is mostly right-handed. It's a slight preference to be right-handed because it's governed by the weak decay, because anti-muons are only going to be produced from a pion decay with right-handed spin, whereas muons produced from pion decay are only going to be produced left-handed, right? And so this is the hypothesized kind of interaction, is that you have muons that come in and preferentially destroy the left-handed interaction, right? And so even if you could make 50-50 on Earth all the time, positive right-handed muons have an extra interaction chance for these kinds of molecules over this one. Now, it's very slight. The hypothesis is that it's a very slight amount, but it's not an amount that that is over many millions of years or billions of years. It impacts the kinds of impacts the evolution of the biology, right? And so that could be one of the ways we explain homochirality on Earth with life on Earth. So to wrap up here, I just want to show walking through the kinds of things we talked about with the astroparticle lens. We have somewhere in the universe the extreme accelerators producing cosmic rays at ridiculously high energies, and those cosmic rays travel to Earth and can pass through our heliosphere and make it to Earth where we make measurements. But at Earth, we're also shielded by that atmosphere, right? And we have interactions that produce muons on the surface, which might be related to why we observe this homochirality in our DNA. But in order to survive our trip back to space, right, we have to deal with that radiation. So this is how, with the astroparticle lens, we can learn how to survive in space, but even maybe find out how we got here. And maybe we'll find life on other places as a result of that understanding. Thank you.